All right, in this video, we're going to talk about section 4.9, dealing with antiderivatives. All right, this section will be the last section in chapter 4 in the course. Now, what we're going to be dealing with is, this is just a introduction to something that is a precursor for an upcoming chapter that deals with integration. And here, we're going to be dealing with antiderivatives. Okay, so the goal of differentiation is to find the derivative, or f prime, of a given function f. Now we're going to reverse the process, which is called anti-differentiation. Okay, so here we're going to be given a function f, and we're going to be looking for an antiderivative of the function called capital F, whose derivative is f. That is, a function f such that f prime, capital F prime, would be equal to lowercase f. So this is the definition of what an antiderivative is, okay? A function f is an antiderivative of lowercase f on an interval I, provided f prime of x is equal to f of x for all x in I. Okay, so now we're going to be thinking backward in this case. Okay, you'll be given a derivative, so you want to find out what the original function started off as. Okay, let's consider this derivative formula, which is the derivative of x with respect to x equaling to 1. Now, it implies that the antiderivative of f of x equal to 1 will have to be capital F of x equal to x, because if I take the derivative, which is f prime of x, that would give me f of x. All right, using that same logic, we can say here that the derivative with respect to x of x squared would be 2x. And that would imply that its antiderivative of f of x equal to 2x would be capital F of x equal to x squared. And the derivative with respect to x of sine of x would be equal to the cosine of x. That will imply that the antiderivative of f of x equaling to cosine of x would be capital F of x equal to sine of x. Okay, now these proposed antiderivative formulas can be checked by showing that f prime equals to f. Now, an immediate question is going to be this: does the function have more than one antiderivative? All right, so to answer that question, we're going to focus on f of x is equal to 1 and the antiderivative, capital F of x equals to x. And because the derivative of a constant, which is capital C, is equal to 0, we can see that capital F of x is equal to x plus c. That's also the antiderivative of f of x equal to 1. And of course, we can easily check that by taking its derivative with respect to x of x plus c, and that would give you 1, which is lowercase f of x. Okay? So that means here that f of x equals to 1 does have an infinite number of antiderivatives. Okay? So what that means here is this: since, of course, f of x does equal to 1, capital F of x, we know, is going to be x. And it could be something like x plus, let's say x plus 5. Or it could be f of x is equal to, let's say, x minus 1,000. Okay? That constant could be any real number. But both of these, if you take the derivative of both of these, you're going to get f of x is equal to 1. It's a derivative. Okay, so here this brings up the family of antiderivatives, which is at the bottom of your handout. It says here, let f be any antiderivative of f on the interval I, then all of the antiderivatives of lowercase f on I have the form capital F plus c, where c is an arbitrary constant. Okay, so when we deal with antiderivatives here, we're going to include plus c. Okay, because they will have the form capital F and then plus some constant. We don't know what that constant is, but it can be any real number and it can be any arbitrary constant. Take a look at example 1 on the next page. Here we want to use what we already know about derivatives to find all the antiderivatives of the following functions, like f of x is equal to 3x squared. Okay. Well, we're going to have to think about this for a moment here. We have to think about the fact that for 3x squared, I know x cubed would give me when I take the derivative of x cubed, I would get 3x squared. So that means that capital F of x would be equal to x cubed, and then plus some constant c. Because if I take the derivative of x cubed, I would get 3x squared. Now, what about f of x lowercase f of x is equal to 1 over 1 plus x squared? Well, back in chapter 3, we did talk about trigonometric functions here. In fact, more specifically, inverse trigonometric functions here. So if I have lowercase f of x is equal to 1 over 1 plus x squared, then some trig function, when I take the derivative of that, would give me this back. And that would be the inverse tangent of x plus some constant c. And then lowercase f of t is equal to sine of t. Well, one of my trig functions says here, there's a relationship where if we have the derivative of, let's say, the cosine, I would get negative sine of t. So let's use the cosine of t plus c. But notice that sine is positive. The derivative of the cosine would give me negative sine of t. So in order for that to be positive, that means that the cosine of t has to be negative. And you can check this by taking the derivative of the cosine of t. The derivative of the cosine of t is negative sine of t, and then the negative in front will make that positive sine of t. Okay. All right, now let's talk about indefinite integrals here, okay? Because these are what we call indefinite integrals that we're going to be looking at that include plus some constant. That is if I can. Okay, there we go. Okay, now the notation that the derivative with respect to x of f of x means take the derivative of f of x with respect to x. Now we're going to need analogous notations for antiderivatives for historical reasons that become apparent in chapter 5. The notation that means find the derivative, the notation that means find the antiderivative of x is the indefinite integral. And this is the notation. This symbol right here is an elongated s. Okay, and it actually means the sum. So here, that would be your integral sign, and then f of x dx. So every time an indefinite integral sign appears, it is followed by a function called an integrand, which in turn is followed by the differential dx. But now dx simply means that x is the independent variable or the variable of integration. The notation, the integral of f of x d of x, represents all the antiderivatives of the function lowercase f. When the integral is a function of a variable different from x, let's say g of t, then we write that as the integral of g of t dt to represent the antiderivatives of g. Okay. Now, let me go ahead and review the parts of the integration here. Okay. So here, if I have something like this, the integral of f of x dx, that's going to be equal to capital F of x plus c. So here's the parts that are in this integral notation. The elongated s that you see here, that would be your integral sign. The f of x that you see here, we call that the integrand. And then dx, that's called the variable of integration. The variable of integration. And it could be something like dx or dt or dy or whatever. Capital F of x, of course, that would be your antiderivative. Antiderivative. And the capital C, that's called the constant of integration. So again, with your indefinite integrals, when you do those integrals, you must include plus c. Okay. All right. All right, so now if we were using that new notation, then of course, the integral of 3x squared dx that we looked at was x cubed plus c. And the integral of 1 over 1 plus x squared dx will be the inverse tangent of x plus c. And the integral of sine of t dt would be negative cosine of t plus c. All right, so now let's first start off with a couple of theorems here. One of them, well, actually, 3 different rules to be exact. One of them will be the power rule for indefinite integrals here. Now, this is similar, this is just the reverse of the power rule for derivatives or differentiation. Okay, because if you recall back in chapter 3, we did talk about the power rule for derivatives. You always bring the power down in front of the variable or expression, copy the expression over to the 1 less power. Well, we're going to do the reverse of this. Okay, so if we have the integral of x to the p dx, what you're going to do here is add 1 to the power and then divide that by that new power. That's x to the p plus 1. That's divided by the new power, p plus 1, and then include plus c. The restriction here is this, that p, which is your exponent, can't be equal to -1. Your p cannot be equal to -1 in this case. So, and that's if p was equal to -1, then that means that this function, f of x, would be undefined. Okay, and later on, we're going to talk about something where f of x is equal to x to the -1, and you take its integral. Okay, we'll talk about that later. All right, now, any indefinite integral calculation can be checked by differentiation. So the derivative of the alleged indefinite integral must be equal to whatever your integrand is. Okay. All right. Now we do have a constant multiple rule and the sum rule for integration as well. Somewhat similar to taking derivatives for a constant multiple rule and the sum indifference rule, I should say, as well. Starting with the constant multiple rule, that's going to be this. The integral of some constant c times f of x dx is going to be this. I can pull the constant out in front of the integral symbol. So it'll be c times the integral of f of x dx. And that's going to be for some real number c. And of course, the sum rule, that's going to be the integral of f of x plus g of x dx. Here I can break this apart and take the integral of each part, like the integral of f of x dx plus the integral of g of x dx. And this also works if this was a minus sign as well. Okay? Because it's like adding a negative as well. Okay, so now we're going to apply those three different rules here to these examples. Starting with example 2. Let's determine the following indefinite integral, and let's say we want to check by differentiation. So in this case here, I got the integral of 5x to the 9th minus 7x to the 13th dx. And I want to find its integral. All right, in this case here, let's go ahead and first use the sum rule here. Actually, it should say the sum and difference rule by breaking this apart, because I can take the integral of each term. So here I can do the integral of 5x to the 9 dx minus the integral of 7x to the 13th dx. And then next, I'm going to use the constant multiple rule by bringing the constant out in front of the integral sign. So I'm going to pull the 5 out in front, and that'd be multiplied by the integral of x to the 9 dx minus, pull the 7 out in front here. I have 7 times the integral of x to the 13th dx. And now what we're going to do here is find the integral of each one of these. So if I bring down the 5, here I increase the power by 1. So it'll be x to the 9 plus 1, which is 10. Divide that by the new power, which is 10. That goes in the denominator. And then minus 7 times this. Add 1 to the 13. We increase that power by 1. That'd be x to the 14. That'd be divided by that new exponent, which is 14. And of course, since I'm taking an indefinite integral, I have to include the plus c. Leave off the plus c. Usually in my math lab, they're going to count it wrong. On a paper and pencil test, if I give one like that, you leave off the plus c, you'll lose points. At most, 1 point. Okay? Now, let's simplify this a bit. Let's see, if I divide 5 into 10, that's going to go 2 times. The 2 will be in the denominator. And then 7 goes into 14 2 times. That 2 will be in the denominator as well. So that means I'm going to end up with, let's see, x to the 10th divided by 2 minus x to the 14th divided by 2, and then plus c. And of course, we can check this by differentiation. And I'm going to have to do the check on the second sheet of paper. Let's see here. So here I got x to the 10th divided by 2 minus x to the 14th divided by 2 plus c. So this is capital F of x, I should say. And then capital F prime of x, if I take its derivative, it'll be this. Bring down the 10. Copy the x down to the 1 less power, that would be 9. That's divided by 2. Minus, bring down the 14. Copy the x down to the 1 less power, which is 13. over 2. And then the derivative of a constant is 0. So that means 10 divided by 2 will be 5. So I have 5x to the 9th minus 14 divided by 2, which is 7x to the 13th, which is the same as this integrand that I came up with. So that means I've taken that derivative, taken that integral correctly. And if I want to, since the denominator is 2, I have the same denominator, I can put the x to the 10th minus x to the 14th, all under that denominator of 2, and then plus c. And that would be what the integral of 5x to the 9th minus 7x to the 13th dx will be. All right, take a look at example 3. In example 3, we're going to evaluate the following indefinite integral. Here we got the integral of 7 over the square root of x plus 7 times the square root of x dx. Let me write this using negative exponents here. If you recall that the square root of x in exponential form will be x to the 1/2 power. So that's what I'm going to do here. Bring over the integral of 7. Now, x square root of x is x to the 1/2, but since it's in the denominator, if I take that out of the denominator, it will be x to the negative 1/2 power plus 7x to the 1/2 power. And now we're going to go ahead and use, and I need to put this in parentheses and include dx. Now let's go ahead and use the sum rule. So the sum rule is this: I can integrate each term. So it'd be the integral of 7x to the negative 1/2 dx plus the integral of 7x to the 1/2 dx. And in this case here, use that constant multiple rule by bringing the 7 out in front. So it'll be 7 times the integral of x to the negative 1/2 dx plus 7 times the integral of x to the 1/2 dx. And now we integrate each one of these. So I'm going to bring down the 7, copy the x over, and add 1 to the negative 1/2. So negative 1/2 plus 1 would be positive 1/2. And then that's divided by that new exponent, 1/2. Plus, bring over the 7, bring down the 7. For the x, I increase the power by 1. So 1/2 plus 1 would be 3 over 2. All divided by 3 over 2. And then plus c. All right, so simplify this a bit. This is 7 divided by 1/2, which is the same 7 times 2, because the reciprocal of 1/2 is 2. 2 times the 7 will give me 14. So it'll be 14 x to the 1/2 plus the reciprocal of 3 over 2 will be 2/3. So 2/3 times 7 over 1 would be 14/3 times x to the 3/2, and then plus c. Now, I believe in the homework, they might just want you to leave it like this using just rational exponents. Okay. All right, let's look at another example, example 3 on the next, example 4 on the next page. And that's this. Let's say we want to find the integral of 3 over s squared minus 4s squared ds. Now here they're using s as the variable. not x. They're using s here. So if I was to use the sum rule, this is what I'll have. The integral of 3 times, I'm going to write s squared using negative exponent since it's in the denominator. I'm going to take that out of the denominator. It'll be s to the negative 2 minus, well, this is going to be ds, by the way, minus the integral of 4s squared ds. All right, let me get rid of this left parentheses here since I don't need it. There we go. Now let's use that constant multiple rule by pulling the 3 out in front. So it'll be 3 times the integral of s to the negative 2 ds minus, pull the 4 out in front, it'll be 4 times the integral of s squared ds. And then use the power rule on each of these. So in this case here, this will be 3 s to the negative 2 times negative 2 plus 1. We add 1 to that. It'll be negative 1. That's going to be divided by that new power, which is negative 1, minus 4. And then for the s, we increase the power by 1. So 2 plus 1 would be 3, divided by the new power, which is 3, plus that constant c. So if I simplify this, 3 divided by negative 1 would be negative 3. And that s to the negative 1, I'm going to pull that in the denominator to make that a positive, well, s to the positive 1 power. So just be s minus, let's see, 4 divided by 3, that's just going to be 4/3. S cubed plus c. And that will be as far as I can go with that problem. So that's the integral of 3 over s squared minus 4s squared. All right, now example 5. Here's example 5. Here we got the integral of 6x to the 5th quantity squared dx. Now to start this problem, I will have to go ahead and expand 6x to the 5th, 6x plus 5th plus 5 quantity squared. 6x plus 5 quantity squared, I need to expand that by just multiplying that out. So 6x plus 5 quantity squared, I can write that as 6x plus 5 times 6x plus 5. And then apply the FOIL method. And that FOIL method is this: first term times the first term. 6x times 6x, that's 36x squared. The outer 6x times the plus 5 would be plus 30x. Inner 5 times 6x would be plus 30x, plus the last times the last 5 times 5. That'd be 25. And then combine like terms, I'm going to get 36x squared plus 30x. No, 30 plus 30 is 60x. I need to combine like terms. So that's going to give me 60x plus 25. All right, so in this case, here's what I'll have. And that is the integral of that 36x squared plus 60x plus 25. And that would be, in this case, dx. Now I'm going to go ahead and just use that constant multiple rule and the sum rule on this next line here. So I know I'm going to have to pull out the 36 since it's a constant. That'll be multiplied by the integral of x squared dx plus, let's pull the 60 out in front. That'd be the integral, 60 times the integral of x dx plus, I'll pull the 25 in front. That'd be multiplied by the integral of 1 dx. So here, the integral of x squared, I add 1 to the power. That'd be x cubed, and that'd be divided by that new power, which is 3, plus 60 times, this is x to the 1, so I add 1 to that power, it'll be x squared divided by 2, plus 25 times, the integral of 1 dx would simply be x, and then plus c. Now, if I simplify this a bit, if I divide 3 into that 36, that would go 12 times. And if I divide 2 into 60, that's going to go 30 times. So I'm going to end up with 12x cubed plus 30x squared plus 25x plus c. So that's the integral of 6x plus 5 quantity squared would be 12x cubed plus 30x squared plus 25x plus c. All right, example 6 looks like this. Here we got rational exponents here. The integral of 3x to the 1/3 plus 5x to the negative 1/3 plus 6 dx. Okay, in this case, I'm going to go ahead and use that constant multiple rule and the sum rule all together. So here's what I'm going to have. Well, let me pull the 3 out in front before I do anything. Using that constant multiple rule, I'll pull the 3 out in front times the integral of x to the 1/3 dx plus, let's pull the 5 out in front times the integral of x to the negative 1/3 dx plus 6 times the integral dx. And now let's take the integral of x to the 1/3 dx. So I bring down the 3. For the x, I increase the power by 1. So 1 plus 1/3, that'd be 1 and 1/3, but as an improper fraction, it'll be 4/3. That'll be divided by 4/3. And then plus, bring the 5 down, increase the power by 1. Negative 1/3 plus 1 whole. Well, 1 whole is 3/3, but if you add negative 1/3 to that, it will be 2/3. So I have x to the 2/3 divided by the new power of 2/3 plus the 6 integral of, and this should be 1 dx, doesn't matter. Integral of 1 dx will just be x. And then plus c. Now, in this case here, if I do 3 divided by 4/3, I'm doing this out to the side, 3 divided by 4/3, that's saying 3 times its reciprocal, which is 3/4. 3/1 times 3/4 will be 9/4. So I'm going to have 9/4 times x to the 4/3 plus, and then 5 divided by 2/3. That's like 5/1 times 3/2, the reciprocal of that, which is going to be 15/2 times x to the 2/3 plus 6x plus c. Okay. That would be what the integral is. Now it does say check the work by differentiation. So here's what the check would look like. If I take the derivative with respect to x of 9/4 x to the third, x to the 4/3, plus 15/2 x to the 2/3, plus 6x, plus some constant c, I'll get this. Bring this power down, 4/3 times 9/4. Now, if you do 4/3 times 9/4, 3 goes into 9 3 times, the 4's divide out, you'll be left with 3. So this will be 3, bring the x over to the 1 less power. 4/3 minus 3/3, that will be 1/3. Plus, bring this power down for 2/3 times 15/2. Well, 2's divide out. 3 goes into 15 5 times. So this will be 5 x to the 2/3 minus 1 whole. That would be negative 1/3. Plus the derivative of 6x is 6. The derivative of a constant is 0. So this should be the same as that integram that I started off with. 3x to the 1/3 plus 5x to the negative 1/3 plus 6. So that means I did this integral correctly. All right, let's look at the next example on the next page. And again, we can check our work by differentiation. The integral of 6 times the 9th root of x dx. 6 times the 9th root of x dx. So I'm going to write this using a exponential form here. So I can bring out the 6 in front. The 9th root of x in its equivalent exponential form will be x to the 1/9, because that x has the exponent of 1. That's the numerator. The index of 9 will be your denominator. So you have 6 times the integral of x to the 1/9 dx. And now we can take the integral of x to the 1/9 by adding 1 to the exponent. 1 plus 1/9, that will be 1 and 1/9, but it'll be 10/9 if we write that as an improper fraction. So I have x to the 10/9 divided by 10/9, and then plus c. Let's see, if I do 6 divided by 10/9, that would mean 6/1 times its reciprocal, 9/10. Well, I know a 2 can go into that 6 3 times, and a 2 can go into 10 5 times. So 3 times 9 would be 27/1 times 5, which would be 5. So this would be 27/5 x plus c. And I should say x to the 10/9. Can't leave that off. Let's see. Yeah. 27/5 x to the 10/9 plus c. And now to do the check, take that derivative. The derivative with respect to x of 27/5 x to the 10/9 plus c. Well, if I bring the power down, that would mean 10/9 times 27/5. Let's see, 9 goes into 27 3 times. 5 goes into 10 2 times. 3 times 2 would be 6. So this would be 6. Copy the x over to the 1 less power. 9/9 from 10/9 will be 1/9. And of course, the derivative of a constant is 0. So if I write that in radical form, this will be 6 times the 9th root of x, which is the same thing here. Okay, next is example 8. Let's say I want to determine the following indefinite interval. Let's say I have 3x cubed minus 6x squared divided by x dx. Well, in this case, I'm going to divide each term in the numerator by the denominator of x. So I'm going to break this up as the integral of 3x cubed divided by x minus 6x squared divided by x, and then dx. So I have the integral of 3x cubed divided by x will be 3x squared minus 6x squared divided by x. That'll be 6x dx. And then I'm going to use a combination of the constant multiple rule and the sum rule here. Pull the 3 out in front. That'll be multiplied by the integral of x squared dx minus, pull the 6 out in front of that integral, be 6 times the integral of x dx. Okay. And now next we're going to take the integral of each piece. Bring the 3 down, increase the power by 1 for the x, will be x cubed divided by 3, which is your new exponent, minus 6 times, increase that power by 1 for this x to the 1. 1 more than that would be x squared divided by that new exponent of 2. And then include the plus c. Now, if we simplify this, if I divide out the 3's here, and if I say 2 goes into 6 3 times, I will end up with x cubed minus 3x squared plus c. Okay, and that's the integral of 3x cubed minus 6x squared, all divided by x will end up being. Okay. All right. Do look out for part 2 of this video on section 4.9 dealing with antiderivatives.